Hello everyone, welcome to what will be pre-lecture 21. I'm going to talk more about enthalpy today, in particular how we can use enthalpy to better understand chemical reactions. So with that, last class we talked about basically why does forming bonds release energy, and I told you that they do release energy. Just a reminder that bonds release, or when bonds form, they release energy because we get a basically stabilization of our potential energy because our electrons and protons are attracted to each other, and so our molecule, in this case dimethyl ether, is going to be more stable when we're able to share those electrons in the form of bonds than it would be with just all of these atoms existing as pure elements in the gas state. Okay? So we talked about that. We defined what enthalpy is. Just a reminder, that's our delta H. And oftentimes in chemistry, we're concerned about the system, which is a chemical reaction most of the time in chemistry. And things that release energy are called exothermic. We have a negative delta H. Things that absorb energy, heat energy, are have a positive enthalpy for the system. Okay. So if we think about applying these sorts of things to reactions then, just a reminder that any reaction we have, we're going to have to break bonds on our reactant side. So we have CH4 and O2 in this reaction shown here. We have to break the CH bonds and break the OO bonds in our reactants. And then we have to form bonds in our products. So we have to form CO bonds on our product side and form OH bonds on our product side. And again, just a reminder for the framing of this that if we apply the first law of thermodynamics, that the change in energy of our system, so if we release energy here, that energy is going to be absorbed by our surroundings, or if we lose energy in our surroundings, that's going to be absorbed by our system, and that when we add all of those up, our energy can be neither created or destroyed, and so our change in energy has to equal zero, right? Which is essentially, these two equations are saying the same thing, okay? So let's start applying this to chemical reactions. And so say we have this reaction here where we have 2H2 plus O2 makes 2 molecules of water. And our delta H of our reaction for that, I would tell you, is that it is an exothermic reaction with an enthalpy of negative 483.64 kilojoules for every mole of the reaction that we perform. Okay? If we were to double the scale, so if we were to multiply all of our coefficients in this first reaction by 2, that would also double the amount of heat that would be released. That should make some amount of logical sense, where if we have more stuff to burn, in this case, more hydrogen gas to burn, that is going to ultimately release more energy, right? If we were to run the reverse reaction, so if we were to start with water, and split water into H2 and O2, so this is just the reverse of our first reaction up there, what happens is we actually get a reversal of our sign here. So you'll notice the number is the same, the 483.64, but now this reaction, instead of being exothermic, is now endothermic with the positive delta H. Okay? So just wanted to orient you on those, make sure we have an understanding of how enthalpy changes based on the scale or the direction of our reaction. Enthalpy itself is also something called a state function. And so that means that it only depends on the state of the system in that particular moment. It doesn't matter the history. And because of this, we can actually use this to break the bonds in our molecules from any reaction into the gas phase and then recombine them in the gas phase to form our products. And so let's go through an example of this. So say we have this chemical reaction where we have H2 plus Cl2 makes 2 HCl. We could, as a first step, break the bonds between H2 and Cl2, and so if we broke those bonds, we would end up with 2 moles of H atoms in the gas phase, 2 moles of Cl in the gas phase, and then we would take those, recombine them to make 2 moles of our product, HCl. And so with that, we could look in the back of our textbook. I put the table here, so for all the problems in this chapter, if you ever need values for gas state enthalpies, look in table B13 in your textbook appendix. And to break those bonds, anytime we break bonds, that's going to be an endothermic process, right, in order to break those bonds. So we know these delta H values are going to be positive. So we'd have positive 243.4 for breaking chlorine, positive 435.3 for breaking hydrogen. And then when we add those two up, so the total chemical reaction there, we're just adding those values to get 678.7 kilojoules per mole for our reaction. Then, when we make bonds, we put those two things together, and again, getting values from our table, we would get this 8 negative now because we're bond forming. So when we're forming bonds, that's going to be a negative 863.2 kilojoules per mole. And so if we want delta H of our reaction in total, we just add our bond breaking and our bond making enthalpies up. And in this case, this process is exothermic overall. This reaction is exothermic because we end up with a final enthalpy value of minus 184.5 kilojoules per mole. Okay? So we can also save some time making thermodynamic measurements if we use a standard set of conditions. This is what scientists determined a while ago. And so we have this idea of standard conditions. And the standard condition of something is when we are making measurements for elements and their compounds. So for example, O2 is a compound despite being a pure element at 25 degrees Celsius and 1 atm. And we haven't explicitly talked about atm, but it is a measure of pressure. It's basically atmospheric pressure, we could say. And these values that are measured under standard conditions, anytime that's the case, it's denoted with a degree sign. And so, for example, the enthalpy of formation here is delta HF with our degree sign by the enthalpy, and that means it is under those standard conditions. And so when we have delta HF, or our enthalpy of formation, that means we are forming 1 mole of a compound from its elements. Again, it has to be in its elemental form in their most thermodynamically stable state, aka how we would find them at 25 degrees Celsius and 1 atm. Okay? So here's a little knowledge test for you. Which of the following equations describes a reaction in which delta H standard is equal to the enthalpy of formation? And so if you want to pause the video, think about that, you can, but I will go ahead and reveal the answers now. So out of these 4, both option A and C are describing reactions where we're looking at delta H of formation because we are starting with elemental forms, so pure elements, both magnesium and oxygen, or magnesium and carbon and oxygen, and then we're combining to form 1 mole of product. The reason option B wouldn't be accurate is because we start with magnesium oxide and CO2. Those are not pure elements, and so we can't count them. And the reason option D isn't true is because we're starting with magnesium and oxygen in the gas phase. So this would be if we were combining the atoms like we did earlier in this video. And hopefully we know, because we've done it in lab already, magnesium, definitely not a gas at 25 degrees Celsius and 1 atm. Okay, so that is our enthalpy of formation. Last thing I want to cover in the pre-lecture video is talking about Hess's law. And so Hess's law is another way for us to do kind of our energy accounting, where if we want to find the enthalpy of a reaction, that's going to be the same regardless of the path that the reactants take to become products. Again, this goes back to enthalpy being a state function. So we can calculate delta H of a reaction by adding enthalpies associated with a series of hypothetical reaction steps. And so let's do an example of that. Before we had methane, or natural gas pipelines. Some cities would produce what they called town gas, and so this was a form of fuel where we start with carbon and add water, and you can produce CO and H2. And so our task is calculate the reaction enthalpy, and I would also give you this information below here. So we have these 4 reactions, and you can piece these together either by turning some around, multiplying some by coefficients, but our goal here is to get these 4 reactions to add up to produce this one reaction here, okay? So I would recommend giving yourself time to try this before class, but this is where we're going to be starting class on Friday. So give it a try so you're a step ahead when we get there, but this will be where we start class on Friday, okay? That's all for the pre-lecture video. Hope it was useful. If you have any questions, please do let me know, and I will see you soon.